everyone, and welcome to lesson 23.2, part 1. Today's lesson is actually going to start a little bit with 23.1. We're going to talk briefly about a couple of things on page 304, and then we'll move into 23.2, part 1. So, on page 304, we're going to start here with number 5. And what we're looking at with number 5 is we're checking out, do these identities hold true? Would this statement be a true statement? Is this an identity or not? So one way we could do that is by checking out, okay, sine of 90 plus 60. Does that equal sine of 90 plus sine of 60? What we're going to see, that's not true, right? This doesn't hold true. Nor does part B in number 5. If we were looking at radians, gradient values, if you look at cosine of pi over 3 minus pi over 6, and we compared that again to cosine of pi over 3 minus cosine of pi over 6, we see that these values are not the same. So what we can basically justify here is just having an addition or subtraction inside of sine and cosine doesn't necessarily mean that if we break them apart into individual statements that they will be true. Okay, now that's where we get into the looking at deriving a formula that does work, and it goes back to using some similar triangles in a whole lot of algebra. So that eventually what we get with these similar triangles and the algebra is the difference identity for this cosine value of alpha and beta, or sometimes we call those x and y. And what the formula basically comes out to be is that the cosine of alpha, or x if you want to call it that way, times the cosine of beta, or y, plus the sine of alpha, or x, times the sine of y, beta, that is what cosine of alpha minus beta, or x minus y, would be. Okay, so if we tested this out with the examples that we had before, if we did sine of 90 plus 60, we could say, okay, cosine of 90, excuse me, we'll use the subtraction one because we're in radians. We'll do cosine of pi over 3 times the cosine of pi over 6 plus the sine of pi over 3 times the sine of pi over 6 would give us the same value as what cosine of pi over 3 minus pi over 6 was, right? So we do actually get that equality that we were looking for before. Okay, so from this piece to this piece. Now, that is, those formulas are going to translate. So we talked about the cosine minus, right? And how this was a plus sign. If it's a plus sign in here for cosine, then it's a minus sign in here. And this is now at the beginning of 23.2 on page 307. Jump forward a little bit. And the sign then, if there's a plus sign in here, it's a little slightly different formula. It's sine of alpha cosine of beta plus, so the sign is the same, sine beta cosine alpha. And then the minus sign here, we have the minus sign here. So the sign ones stay the same. And then we have tangent as well, where if it's a plus sign, then it's a plus sign here, but a minus sign down here. Or the tangent, we have a minus sign down here, so minus plus, okay? And these are your sum and difference identities that you're definitely going to want to have written down. Now, from here, as we again look here, if this is a plus sign, this is how you would read it there and there. And then the tangent ones, we have minus, minus, plus. Okay. Now, how are we going to actually use these? That's what's moving on to page 308 and some examples using these. So we, first off, actually at the bottom of page 307, have an identity that we can prove now using this information. So similar to what we were doing in activity 21, we're trying to prove that this ultimately has a final answer of this. So we have alpha and we have beta, or sometimes we call those x and y. So when we plug this into the formula, we know that it is sine of alpha, so x, times the cosine of beta, which is pi over 3, and then the sign stays the same in here. So if this is a plus sign, this is a plus sign. Now we have cosine of alpha, which is again x, times the sine of beta, which is pi over 3. And if we start simplifying this, we know that cosine of pi over 3 is 1/2. And then we know that the sine of pi over 3 is 3 pi, square root of 3 over 2, which, if we just moved those values to the front, we would have the 1/2 sine x plus the square root of 3 over 2 cosine x, which checks out our identity. So we can use these in identities now to prove what something simplifies to. We can also use this to find exact values of these non-special angles. So angles that are not necessarily on our unit circle, but we can derive them using values of the unit circle. So for instance, sine of 15 could be used as 60 minus 45. Okay, you could rewrite that. You could also use other values that when you subtract them are 15. So now we're going to substitute those in for alpha and beta, right? We have alpha, we have beta's 45, and we're plugging that into our formula. Now all of these values do come from the unit circle. Sine of 60, cosine 45, sine 45, and cosine 60. And as simplified as these are going to get is the square root of 6 over 4 and the square root of 2 over 4, which we can combine into one exact value with a common denominator, okay? So if we look at this using cosine of 105, again, you have some options of what you want to do. I'm going to choose to use cosine of 60 plus 45. And again, here is my alpha, here is my beta. And if I plug into the formula, cosine, expanded here, cosine beta minus, remember the sign is going to flip-flop for this cosine, and then it's sine alpha, sine beta. So again, now I can just plug in 60 for alpha and 45 for beta into the formula, and I know that the cosine of 60 is 1/2, cosine of 45 is square root of 2 over 2, sine of 60 is square root of 3 over 2, sine of 45 is square root of 2 over 2, and if we simplify, we get square root of 2 over 4 minus the square root of 6 over 4, which can be rewritten as one singular fraction. Now, for part B, sometimes it is easier to look at this as a fractional value. Sometimes you might just want to convert this to degrees, because we know that 3 pi over 12 and 4 pi over 12 add up to be 7 pi over 12, and those are actually values from our unit circle. So pi over 4 and pi over 3. Right? We could divide those up. But if fractions are not your thing, say you didn't want to look at those as fractional values, you always have the option to convert this to degrees, because we know that to convert this to degrees, we need to multiply by 180 over pi. So we would end up with 7 times 180 over 12, which is again 105 degrees. Okay, so you can convert these to degrees if you're not comfortable with the radian measures. Now I'm going to go back to using, however, the radian measures just to show you. So we said pi over 4 and pi over 3 added together would equal our sine value there. And again, when we're using the sine formula, it's sine of alpha cosine beta, same sign here, plus cosine alpha times the sine of beta. So again, if we have alpha is pi over 4 and beta is pi over 3, plug in the pi over 4 and the pi over 3, and then simplify from there. We have the square root of 2 over 2 times 1/2 plus the square root of 2 over 2 times square root of 3 over 2, which again is going to simplify to be one final answer of square root of 2 plus square root of 6 over 4. Okay. Finally, we have the tangents, and the tangents can get a little ugly because of the simplifying. Now, to get 75 degrees using values from our unit circle, we can say 45 plus 30, right? And tangent is a little bit more complicated because it's tangent alpha and then same sign as what's inside of here. So tangent of beta all divided by 1 minus tangent of alpha tangent of beta, right? And again, this time it's going to be opposite sign of what was in here. That's how tangent goes. Now again, we have alpha and we have beta. So 45 and 30, 45 and 30. Now tangent of 45 is just 1. Tangent of 30, however, is the square root of 3 over 3. And then we have 1 minus 1 times square root of 3 over 3, which is just square root of 3 over 3, right? Now this is some ugly stuff going on with some, numbers running around all fractions within a fraction. So one way we can get rid of that denominator of 3 in both here and here is by multiplying everything by a 3. Because what happens is if we distribute that 3 to everything, we end up with 3 plus the square root of 3, because our denominators would cancel. And then 3 minus the square root of 3, because we have 1 times square root of 3 over 3, distribute the 3, they canceled again. So now this is slightly more manageable. But it's officially still not fully rationalized to be our final answer because we have a square root in the denominator. So the next piece of this is multiplying the top and the bottom by the conjugate of the denominator, which in this case is going to be, if we look here, we can multiply first times first, last times last. So we end up with 9 minus 3. And then in our numerator, we have a little bit longer route because they're not conjugates, so we'd have to double distribute. So we end up with 9 plus 3 square root 3. And then when we distribute the square root of 3, we end up with another 3 square root 3 plus 3. When we multiply square root of 3 times square root of 3, it's just 3. So this finally simplifies to be 9, not 9, 12, because we're going to add the 9 and the 3 to get 12, plus 6 square root 3 when we combine these two. And then finally, 9 minus 3 is 6. It can be simplified one last time to be 2 square root 3, since our 6 can cancel with both pieces. We're just left with 2. So plugging into the formula, not necessarily so bad, but the simplification takes a little bit of work. Please feel free to rewind that to rewatch if you missed any piece. Okay. Now, one way you can always check these in your calculator is by testing out that you simplified correctly. So if I go back to degree mode to test this last one out, 75 degrees. Look at the tangential value of that. Tangent of 75 is going to be approximately the same thing as 2 square root 3. So we see that they're the exact same decimal approximation, so we can check off that all